So how do we use Taylor's theorems in application? Look at this example. We'll build Taylor polynomials of degree 2 to approximate the fourth root of 1 plus x when x is greater than minus 1 near the origin. Do you know what the curve 1 plus x fourth root looks like? So you're interested in using some second degree polynomial to provide a good approximation to the function near the origin. If you get too far, the parabola will not be a very good approximation anymore, right? Not good. Also, too far, you're going to end up approximating the function with a function which is still defined, whereas the fourth root of 1 plus x is not defined anymore. Right? So you have to be close to the origin for this to make sense. You could think of the Taylor polynomials as a generalization of the line of tangency. You're finding the polynomial of tangency at this point, in a sense. So we'll let the function be defined by the following rule. 1 plus x to the 1 over 4. F is defined from minus 1 infinity into a set of real numbers. So we'll pick n equals 2. That means that we have a first derivative. Let's use the rules of calculus for the derivative here, not too complicated, and a second one as well. I'll leave you the pleasure of computing these derivatives. Key takeaway here, they both exist when x is greater than minus 1, and also they are continuous on the interval minus 1 to infinity. That does not include minus 1. We cannot include minus 1 in here because we'd be dividing by 0. So the assumptions, the hypotheses of Taylor's theorem are met. You get out of this that the function f at x is equal to the second Taylor polynomial at x. I'm not specifying f here because it's clear from the context, plus the third derivative, some point c at x divided by 3 factorial, 1 times x minus x0, which turns out to be 0 to the power 3. And if you want to work it out, since we do have the original function, the first and the second derivative, you will find that this is 1 plus 1/4 times x minus 3 divided by 32 x squared plus the third derivative, the x, 3 factorial, x cubed. Right? For this to make sense, you basically need to compute f prime 0. F prime prime at 0. Notice that you have x minus 0 and x minus 0 squared. So that's what you would get here. Now for each x, there's a particular cx here. It doesn't reside just about anywhere. Cx would be somewhere between 0 and x, or potentially x and 0, depending on which side of the origin our specific value of x is. Now, you can use this formula to do approximates. You're trying to approximate this value. That's about the same as you do 0.4. Right? This is exactly f at 0.4. And that's approximately the same as p2 at 0.4. Now, in reality, f at 0.4 is equal to p2 at 0.4 plus this quantity here, where cx is really dependent on 0.4. So I should write this down as, the problem is we don't know what the true value of c at 0.4 is. It's just we know it's some number between 0 and 0.4. So since we don't really know how to compute that, we will just approximate it with the Taylor polynomial of degree 2, which from the previous slide you will remember was 1 plus 1/4 of 0.4 minus 3 over 32 of 0.4 squared. And this value is about 1.085. Now we can't compute the true value of c here, hence we can't compute the remainder. But since we know that c has to be greater than 0 right? Because in this case, x0 was 0, x is equal to 0.4, and c's got to be somewhere between 0 and 0.4, so we know that c is greater than 0. The third derivative, you can actually compute it. We know what the function f is. So you go and you compute the third derivative and you evaluate it at c, you will get the following expression. 21 divided by 64, 1 plus c to the power minus 11 over 4. The calculus problem. Something, you know, or if you want to rewrite it differently, 21 over 64 times 1 over 1 plus c to the power 11 over 4. And c is greater than 0, so this whole thing here is smaller than 1, right? Because we have a denominator here which is greater than 1. So you're dividing by something which is greater than 1, this whole thing will be smaller than 1. So this, the whole, it's got to be smaller than 21 over 64. So then if you use the full formula here, for the remainder, this is going to be smaller than 1 over 6 times 21 over 64, which is what you found here, times 0.4 to the power 3. And if you work it out, it's approximately equal to 0.35 times 10 to the minus 2. 0.0035, roughly speaking. Now what this really says, that the difference between the true value, the fourth root of 1 plus 0.4, and the value given by the approximation, P2, it is going to be quite small. In fact, it is going to be smaller than or equal to 0.0035, which means that this value here is correct for 2 decimal places, at least. A neat application of Taylor's theorem, right? So you do have to understand here, didn't explicitly say it, you take the time to say this. This here, f at x, and this here, P2 at x. So you're looking at f at x minus P2 at x, that is truly equal to the absolute value of this term here, this remainder. Often we will write it like this. What we've done is we've bounded the remainder above by 21 over 64, given what we knew about the situation. Hence, we can bound the error on the approach. There are other uses of Taylor's theorem. This one is so neat. That's all we'll say in these videos.